All right, so today we're going to crack the code that runs the entire universe. And no, it's not written in ones and zeros. It's written in the language of change itself. These are the hidden rules that govern, well, everything, from a simple falling apple all the way to a swirling galaxy. This code, this language, is differential equations. And yeah, we're going to explore it together.
I mean, just think about it for a second, right? Nothing is static. Planets are orbiting, populations are growing, waves are crashing on the shore. So how in the world do you describe a universe that is in constant, relentless motion? How do you even begin to build a mathematical model for a world that never, ever stands still? Well, the answer lies in this incredibly powerful tool, differential equations.
So what are they, really? Well, to put it simply, a differential equation isn't about finding some static, boring number. Nope. It's a rule that connects a thing to how fast that thing is changing. You know, its derivative. In other words, how fast something is changing right now is directly tied to how much of it there is. It's basically the language of cause and effect, just written down in math.
Okay, so to get our heads around this, let's start with the basics. Let's compare this whole language of change to something we all had to learn in school, algebra.
And this really shows a huge shift in thinking. You see, algebra, it usually just gives you a snapshot. It solves for a single fixed value, like x equals 4. Bam, a moment, frozen in time. But a differential equation, oh, that gives you the whole movie. It describes a behavior, a story of how something evolves over time. The solution isn't just a number, it's a function. It's a whole dynamic narrative of change.
So check this out. Let's look at one of the simplest but most powerful rules out there. The rate of change is proportional to the current amount. I mean, that one little idea can describe how a colony of bacteria absolutely explodes in a petri dish, but it can also describe the super precise predictable decay of a radioactive element. The only difference? It's literally just the sign of a single number in the equation, this K constant. It's amazing. One simple rule tells two totally opposite stories, one of explosive growth and one of steady, predictable decay.
But of course, not everything just grows or decays, right? A huge part of the universe moves back and forth in this constant rhythm, this oscillation. Just picture it. You pull a weight on a spring and let it go. It bounces down, then up, then down again. It's oscillating. And this back and forth motion is literally everywhere you look. It's in guitar strings, in the pendulums of old clocks, even in the vibrations of buildings. Now, to capture this, we need equations that look beyond just speed. We have to look at acceleration, how that speed itself is changing. And that's where second-order differential equations come in. They are the perfect tool for describing this kind of rhythm. Here's a cool thing. Every single object that can oscillate has a favorite rhythm, a speed at which it just wants to vibrate. We call this its natural frequency. It's why a short pendulum swings way faster than a long one, or why a thin guitar string has a higher pitch than a thick one. This frequency is baked into the object itself. And this is where things get really, really interesting. And kind of dangerous.
So what do you think happens if you start pushing that mass on a spring? But not just randomly. What if you push it in perfect time with its natural rhythm? A tiny little push every single time it hits the top of its swing. What does the math actually predict is going to happen?
Well, in a perfect system, one without any friction, the math doesn't just predict bigger swings, it predicts swings that grow forever. Unbounded amplitude. The vibration just gets bigger and bigger and bigger, until the system literally tears itself apart.
This phenomenon has a name. It's called resonance. And trust me, this is not just some theoretical curiosity. It's the real-world reason soldiers are told to break step when they cross a bridge. And it's exactly what caused the infamous collapse of the Tacoma Narrows Bridge back in 1940. A steady wind created a force that perfectly matched the bridge's natural frequency, and boom, catastrophic failure. It's a brilliant and terrifying illustration of how a purely mathematical idea can have actual life-or-death consequences in engineering.
Okay, so up until now, we've mostly been talking about one variable, time. But lots of things in our universe change across space, too. To model something like, say, how heat spreads across a room, we need an even more powerful tool. We need to level up to partial differential equations, or what people call PDEs.
Now, these super powerful equations basically come in three main flavors, and each one describes a totally different kind of physical behavior. First up, you've got elliptic equations. These describe systems that have settled down, reached a stable balance. Think of the final steady temperature in a room. Then you have parabolic equations. These are all about diffusion, how things spread out and smooth over time, kind of like a drop of ink spreading in water. And finally, there are hyperbolic equations. These describe waves that travel and keep their shape, like a ripple moving across a pond.
So what this really means is that physicists and engineers have this amazing specialized toolkit for pretty much every type of problem they might face. Whether it's a stable field, a spreading pollutant, or a traveling wave, there's a specific mathematical language ready and waiting, perfectly designed to describe it.
All right, for our last section, let's look at what happens when these perfect mathematical theories slam into the messy, complicated limitations of the real world. Because sometimes the theory itself can create some very strange ghosts in the machine. So there's this really beautiful idea in math called a Fourier series. And you can think of it like a recipe. It says that any complex signal, like a sound wave, for example, can be built by just mixing together a bunch of simple, pure tones, these sine and cosine waves, in just the right amounts. And here's the key part. In theory, if you could use all of them, you could rebuild that original signal with perfect accuracy.
But you knew there was a but coming, right? Here's the catch. In the real world, you can never capture all the data. It's just not possible. An MRI machine, for example, can only measure a limited number of those frequencies. You have to chop the series off at some point. So what happens when you try to rebuild an image that has sharp edges, but you're only using partial information?
Well, you get something called the Gibbs phenomenon. The math itself literally creates these ghostly ringing artifacts right next to any sharp edge in the image. It's an overshoot, a little oscillation that isn't actually there in the thing being scanned, like a person's brain. It is a direct visual consequence of using an imperfect, cut-off mathematical model. It is literally a ghost created by the theory itself.
So let's pull it all together. What's the big takeaway here? Differential equations are, without a doubt, the fundamental code we use to describe our changing universe. They give us the tools to model everything, from growth and oscillation to the flow of energy. They explain the predictable rhythm of a pendulum and, at the same time, the catastrophic collapse of a bridge. And, as we just saw, understanding their limits, like the Gibbs phenomenon, is every bit as crucial as understanding their power, especially when we're talking about life-saving technologies like medical imaging.
And that kind of leaves you with one final big thought. We've used this incredible code to understand so much about our world. But if everything, from the tiniest vibration of a guitar string to the largest structures in the cosmos, is governed by these rules, it just makes you wonder, right? What deeper, more complex equations are still out there, governing the mysteries we haven't even begun to wrap our heads around? What's the next part of the code we're still trying to crack?